Oceania is an enormous archipelago. It includes more than 25,000 islands, some almost as old as the Earth itself. Four and a half billion years ago, the Earth was a ball of liquid matter. There was no surface. Any solid ground was constantly melting back into the cauldron of the Earth's burning core. Scientists had long believed that the first bits of solid crust only appeared when the Earth had cooled down enough. But a recent discovery in Western Australia has turned this concept on its head. Simon Wilde of Curtin University of Technology in Perth has been studying crystals that were formed when our planet was very young. During the formation of the first bits of solid matter, crystallized minerals were formed. These minerals were soon subjected to the most intense volcanic activity in our planet's history. These ancient crystals are called zircons, and it's amazing that the ones Simon has found have survived until today. They are the oldest existing matter on Earth. Their structure can reveal billions of years of history. They are, in fact, the Earth's first historical record.
Zircon requires a granitic rock to grow in, and so it tells us that rocks of granite composition were around 4.4 billion years ago, which is very interesting because previously people didn't believe that continental crust existed at this time, about 150 million years since the formation of the solar system. So this has really changed our view of the early Earth. Instead of being a hot, boiling magma ocean and meteorites banging into it, what we believe now, by 4.4, the Earth had cooled sufficiently to have continents, oceans, and some form of atmosphere. It may well be a CO2-rich atmosphere, but there was an atmosphere nonetheless. This is known as the Dark Ages, because there was no rock record. Now, with the discovery of these crystals, we're actually shining light on those Dark Ages.
The oldest existing crystal on our planet was found in Western Australia. In the 2 billion years since the formation of the Earth, small islands of crust began to emerge on the fiery surface of the planet. When these islands joined up, they formed the first pieces of continental land called cratons. The Pilbara region of Western Australia is one of those ancient continental islands. It is one of the most geologically stable areas in the world. For billions of years, the Pilbara has protected geological treasures that would have been destroyed anywhere else. Few know the Pilbara better than Martin van Kranendonk, who's one of the few persons to have mapped it. He has spent 10 years searching out the rocks that tell the history of Oceania and our planet.
One of the greatest stories about Earth's history is how our planet changed from a very primitive, nasty place where it's very difficult for life to get a foothold to this modern world with its beautiful blue skies and oxygenated atmosphere where life is very complex and abundant. And it turns out that that transition occurred about 2.5 billion years ago. And rocks of that age are beautifully and maybe the best preserved anywhere in the world, just to the north of here, up in the Pilbara region. And we've been studying those rocks over the last few years, and it turns out they have answers to some of these very important questions about how did life evolve and how did we get here?
Martin has found astonishing things in the Pilbara. It was here that he discovered rock formations that may hold the key to understanding how life on Earth evolved from bacteria to us.
little beauties. Isn't that gorgeous? These structures in the rocks here in front of me are called stromatolites. These are structures formed by colonies of living microorganisms. The intriguing thing about these rocks is that although they look a little bit like sedimentary structures you'd see on the beach, normal ripples, which everybody recognizes, these little wavelets when the water moves over the sand, these are actually quite different. When you look at them in 3 dimensions, they are actually cone-shaped. They actually start from a flat level and then start growing upwards, sometimes over tens or even hundreds of meters. And it's these kinds of observations which make us distinguish, or help us distinguish, between physical geology and something that's actually got the signature of early life. And don't forget, these rocks are 3.4 billion years old.
These rocks may be inanimate today, but 3.5 billion years ago, they were very much alive. Although the world they lived in was nothing like the world around us today. At that time, there was little solid ground, and most of what was there was volcanic. The oceans were full of iron and were green. The sky was orange, an atmosphere of methane, ammonia, and carbon monoxide. Not a place for human beings. But it all changed around 1 billion years ago, when the stromatolites colonized the oceans.
At about 2.3, there was a change in the atmosphere from being rich in carbon dioxide and other gases like sulfur dioxide coming mostly from volcanoes to an atmosphere that was building up more and more oxygen. And oxygen is not a naturally forming free molecule. It's a molecule that's produced by life processes, by photosynthesis. And photosynthesis uses our beautiful sunlight energy and water to make body parts, carbon, and then gives off O2.
The stromatolites transformed the atmosphere and left a record of their achievement carved into the rocks.
But this is it right here. This is a transition where we see the real change from early Earth into more modern Earth. At this point, right in this little outcrop section behind me, these rocks hold a story that's as important as the time when the dinosaurs went extinct on Earth from that giant meteorite about 65 million years ago. These rocks are 2.5 billion years, and they record the first time when an early, very sulfurous, gaseous kind of Earth changed forever into a cool, much more modern Earth. And that contact is right down here, where you have deposits of banded iron formation grading up through red-colored iron-rich and gray cherts, and then bang, right there, where I can put my fingernail on the contact, you have the change to modern Earth. And this outcrop is probably the most exciting one I've ever seen in my 25 years of doing geology. It just encapsulates in a few tens of centimeters, this fundamental change when Earth irreversibly became modern.
But the oxygen that was freed by the stromatolites 3 billion years ago did not help what life existed at the time. Quite the opposite, in fact.
When life became more complex and started giving off oxygen, it's actually a pollutant to most of the earlier forms of life. They can't thrive with oxygen. Life evolved to adapt to that new chemical reality. And in fact, because it's harder to make life with oxygen around, life became more sophisticated. But that evolved slowly over time, and only because they actually had to get smarter to live with this pollutant called oxygen around and evolve a more complex way of living.
The stromatolites transformed more than terrestrial life. They also changed the nature of the seas. The oxygen they gave off turned the oceans from green to red. thick deposits of rust lay quietly on the ocean floor until huge tectonic forces thrust them above the surface. These impressive red mountains are now over 1 kilometer high. They are made up of layers of what geologists call banded iron. These are the remains of the massive amounts of rust that lay on the ocean floor. At Shark Bay on the west coast of Australia, the descendants of the ancient stromatolites who reigned over the world's oceans 2 billion years ago can still be seen. A drive of just a few kilometers takes Martin van Kronendonk several billion years back in time. Shark Bay is a haven for a very special type of limestone, an unusual living rock made up of alternating layers of crystallized minerals and blue-green algae.
These structures are called thrombolites, and they're a type of living rock made by colonies of microorganisms. And the amazing thing about them is they just grow like a tree year by year, adding layer upon layer in these beautiful cone shapes, because they're actually growing up towards the light to get the food energy that they need from sunlight. And these structures would have covered hundreds of kilometers of the seabed because there was nothing to graze on them. They were the only living life forms. And they covered the entire oceans and just pumped out this enormous volume of oxygen that eventually changed our planet.
Day after day, the thrombolites at Shark Bay absorb the molecules of water surrounding them, decompose them, and release oxygen. This is the same process used long ago by their ancestors, the stromatolites. To the northeast of Shark Bay is the Hamersley Range. Its massive deposits of iron have attracted prospectors who are digging into the mountains to expose layers of banded iron. If there's enough iron in these core samples, the red hills of Hamersley, oxidized by ancient stromatolites, will be gutted and stripped of their minerals. After 50 years of mining, the Hamersley Range has become almost unrecognizable. 80% of Australia's iron ore reserves are buried here in the Pilbara. One company alone operates 12 mines in the region. The company has built entire towns and constructed a private railway over 1,400 kilometers long. 100 million tons of iron ore a year is taken from the Hamersley Range. Much of it goes to Asia to build cars and cities. In the course of billions of years, other small islands join Pilbara. This ever-widening raft of crust becomes Australia. As time passes, all the other emerging land masses join into a single supercontinent, Gondwana. Australia finds itself welded to Antarctica. This collision of Australia with Antarctica occurs on Australia's south coast, yet the event's consequences reach as far as the middle of the Australian outback. Near the border of the Northern Territory in South Australia, a new mountain range rises up, the Petermann Mountains, with peaks as high as the Alps. After 550 million years of erosion, this is all that remains. This impressive natural wonder is Australia's most famous landmark, Ayers Rock, also known by its Aboriginal name, Uluru. Uluru began its existence as a huge sand dune. Over time, the dune was cemented into a sandstone island. Tectonic forces lifted Uluru, turning it every which way. Some horizontal layers even ended up being vertical. Like an iceberg, only the tip of Uluru is visible. Although it rises to a height of 350 meters, its base extends 6 kilometers below the surface. In the open air, its smooth surface has prevented it from being eroded by wind and water. Collisions between the continents caused a number of cataclysms that transformed southern Australia forever. Jim Gelling of the South Australian Museum is both a geologist and a paleontologist.
Now Ian, for the last run, can you go back just a bit more of an angle? If we went over that vehicle, and we'll go over so I can look...
Jim is returning to the site of an exceptional discovery he made in the middle of Australia's south coast.
You should do, because it'll make more work.
At the foot of the dry Ediacaran hills, Jim and his team found traces of an ocean floor that dried up hundreds of millions of years ago.
When you go back 550 to 560 million years, you're looking at a shallow sea floor with land quite some distance to the west and open ocean to the east. While it's an ocean, sediment keeps accumulating and it keeps a record of everything that's happened during the time of that ocean. But one day, the seafloor will be pushed up into giant folds and pushed into mountains.
As Gondwana formed, the landscape constantly changed. 550 million years ago, the collision of great land masses gave rise to the Flinders Ranges, the largest mountain chain of South Australia. Over time, many of its peaks have eroded and revealed a marine world that existed more than 500 million years ago.
If the Flinders Ranges had never existed, we wouldn't be here, because the only way of actually seeing these layers would be to drill down into the earth, perhaps 500 meters, perhaps 5,000 meters, because every layer would be buried. But it's only when these layers are buckled up and thrust through to the surface that we can see the frayed edges of the sedimentary layers.
Jim and his team have dug up dozens of pieces of ancient seabed. Put together, this marine jigsaw puzzle takes us back 560 million years.
Well, that's what I think. Then down the slope.
We can see the undulations of a vanished sea preserved in sandstone. But the most extraordinary discovery is a rare trace of ancient animal life.
Okay, it's a nice surface.
It's very reminiscent of the bed we have over on the west side.
Yeah.
Mary Drozer is a professor of earth sciences at the University of California, Riverside. She's been working with Jim for more than 10 years.
The reason why this and this
In other words,
need to be the same.
that
No.
actually...
The two researchers believe that the translucent marine animals of Ediacaran mark the beginning of a completely new stage of life on Earth.
But if you get down on your hands and knees, you can see Earth's first experiment in terms of an animal marine community. None of them had backbones. And preservation of soft-bodied organisms is really rare. So when you think about preservation of dinosaurs, what do? We get the bones. We don't get their soft parts. What we see here is we're actually getting soft part preservation. It's like preserving a worm in rock, and that's just unimaginable. But this was a very special window in terms of preservation, and what's so cool about it is that it's Earth's first experiment with animal life.
The Ediacaran ecosystem, brought to life by tectonic movement, continues to surprise the researchers.
Here's another one.
Look at that, Dickinson, seeing the light for the first time in 560 million years.
So that if you look at something like this guy here, this is Spergina, and it's pretty common during this time. And when you look at it, it almost appears to have a head and a body behind. Now, we're not sure. Some people have suggested that actually that's an anchor and it stood up in the seafloor, so we don't really understand it. But certainly, it's got quite a developed and complex body. This trace fossil here, you can see, is just a millimeter in width. This would have been a small organism. We have no idea what made it, but we can see the furrows on the edge that it would have been moving through the sediment. So these trace fossils are really important because it's the oldest unequivocal evidence of bilaterians. And bilaterians, we are interested in bilaterians because we are bilaterians. We are bilaterally symmetrical. And we think in terms of all advanced organisms other than corals and sponges as being bilaterians.
And it gives a bit of cushioning effect too.
Many scientists believe that the Ediacaran marine animals were our most distant cousins. They were annihilated by tectonic movements and environmental changes, but their existence on Earth lasted for more than 40 million years. "250 million years ago, about 1,000 kilometers from the Flinders Ranges, tectonics gave birth to the Blue Mountains. These mountains were sculpted by tectonic forces over a period of millions of years. The steep rock faces and deep valleys are home to several unique species, including millions of giant kangaroos. They're here because of a tectonic movement that may have been the most important event in the history of Australia. Paleontologist Anne Musser works at the Australian Museum. As she makes her way to the bottom of this cave, she is traveling deep into the history of marsupials. She has discovered that the Jenolan caves in the Blue Mountains are literally marsupial graveyards.
Caves are perfect traps. You don't really see the holes. If you're a kangaroo, you're hopping over the top of the surface. You might not see it. You go right down through tubes, through holes, through caves, and you can't get back out again.
Oh my gosh, it's just a little young rock wallaby, very young, slut baby.
The ancestors of these animals made an extraordinary journey.
It is really exciting to be working on these unique Australian marsupials. Their ancestors came from Asia.
150 million years ago, Asia, Antarctica, and India are all still part of the supercontinent of Gondwana. At this time, the marsupials are being driven out of Asia by mammals and dinosaurs. Their survival is only assured when the Antarctica-Australian bloc breaks off from Gondwana. Those who miss the boarding of this tectonic life raft do not survive. However, not all the marsupial species are saved.
Sometime after 50 million years, Australia, as we know it now, broke away from Antarctica, and it took with it that cargo of marsupials. And the ancient platypus and other sorts of monotremes, off it went, the Antipodean arc. The animals on it were to evolve in isolation and become completely unique.
The marsupials of today have little in common with their ancestors. The platypus is one of the last egg-laying mammals, and the kangaroo is by far the largest marsupial on Earth.
As Australia became arid, the animals had to adapt. So you had all sorts of new kinds of animals appearing. The big kangaroos, they're adapted to the dry zone. You've got a lot of animals that have the kind of adaptations that only happen when the environment changes radically. Australia's moving up against Asia, and as that continues, Australia then will move further and further into the Asian zone, into the monsoonal zone, and things will change again. And animals will have to adapt again to another environment. But it's very, very slow. And as that happens, there's time for animals to change.
When Antarctica broke off from Australia, it was pushed by tectonic forces towards the South Pole, a fatal move for the marsupials who lived there. The breakup also permanently affected Australia's south coast. This is the southern edge of the Nullarbor Plain, a 1,200-kilometer-long line of coastal cliffs. It was formed when tectonic forces tore the Australian Antarctic bloc apart. These formations of granite are echoed in Antarctica, the other side of a continental wound that is never healed. After reaching the southernmost point on Earth, Antarctica became the coldest of the continents. Over the millennia, it was covered with thick ice, which has prevented researchers from knowing the exact nature of the underlying mantle. This frozen world is larger than all the land masses of Oceania combined. Needless to say, Antarctica was completely transformed by tectonics after its separation from its Australian sister. In Tasmania, southeast of Australia, the rift left spectacular evidence. At Cape Pillar, the two continental plates separated in an explosion of lava that accumulated on the Tasmanian sedimentary floor. Over time, the sea cooled the lava, which has remained in place ever since. These columns of magma resemble the pipes of the world's biggest organ and are a striking reminder of the separation of the two continents. Since it broke off from Antarctica, the plate that Australia rests upon has been moving northward at a rapid pace, 6 centimeters per year, making it the fastest moving plate on the planet. And it's not a peaceful voyage. North of the continent, the Australian and the Pacific plates are colliding. The perimeter of the Pacific plate is referred to as the Ring of Fire and is one of the most unstable and dangerous zones on Earth.
Imagine that this is the Pacific plate, this is the Australian plate, and the two are in collision. What we have is a slow-motion tectonic car crash. And the result, earthquakes, volcanoes, tsunami, landslides, these spectacular mountains, and more often than not, death and destruction.
Geologist Hamish Campbell is fascinated by the meeting of the Australian and Pacific plates. Astride the rift that separates these two landmasses is New Zealand. On New Zealand's South Island, tectonic forces created an impressive mountain range called the Southern Alps. It's among the world's youngest mountain ranges, the visible face of the clash of tectonic plates.
It's fantastic. What these mountains represent is the very soft westernmost edge of the Pacific Plate, and they are crumpling up. They're being squashed against the much stronger Australian Plate. And they're going up at about a maximum of 10 millimetres a year. And of course, as fast as they're coming up, these rocks are being eroded just as a consequence of normal weather, rain, snow, ice.
Alongside New Zealand's Southern Alps and crossing almost the entire South Island is the boundary between the Australian and Pacific plates. It's called the Alpine Fault, and it's one of the tectonic marvels of the world. Near this fault, earthquakes can occur at any moment. In fact, New Zealand has an average of 14,000 earthquakes a year. When the Alpine Fault shudders, it can lift the Southern Alps several meters in just a few seconds.
Okay, here we are. This is one of the most famous localities in New Zealand geology. This is the Alpine Fault. You can actually see it, it's like a knife cut, and it's literally that line between the green material above and the gravels below. So this is the plate boundary. The gravels represent the Australian Plate, and the overriding green stuff is the Pacific Plate. Those rocks have literally been extruded up from great depths, 20 to 30 kilometres right up to the surface here. And amazingly, we can track that green horizon for pretty much the entire length of the Alpine Fault. So that's in excess of 480 kilometres.
The Alpine Fault is not the result of a frontal collision. The Australian and the Pacific plates are actually sliding violently against one another.
Look at this landscape, it really is chewed up. The fault moves in this sense, okay? So the Pacific side is going south and the Australian side is going north. And it does so, let's see, every time it moves sideways between 7 and 13 metres and vertically between 2 and 4 metres. That's a lot of movement. And it last moved in 1717. We think that on average it moves about every 200 to 300 years, and that's based on a lot of research. Now, 1717 is about 300 years ago, so it's going to move again soon in the future. My colleagues tell me that there's more than a 35% chance of this fault moving within the next 50 years. So that's the forecast. And by the way, we're standing on the Australian Plate here, and that's where I'd like to be. It's actually more stable than the Pacific Plate.
At Punakaiki, on the west coast of South Island, visitors can admire rock formations that resemble stacks of pancakes. These strange layers of limestone were formed deep underwater and were then pushed up to the surface. These odd formations have made Hamish Campbell wonder about the geological history of his country. Could New Zealand have been completely submerged before being lifted above the Pacific Ocean? Although most scientists don't agree with this hypothesis, Hamish thinks it's worthy of discussion.
We know that a very substantial chunk of eastern Gondwana land broke away 83 million years ago and moved off to the northeast. And as it did so, it slowly sank. And it did so for 60 million years.
Although most people are unaware of this, New Zealand is 12 times bigger than it appears if you count the part that's underwater.
We call this underwater continent, Zealandia. And New Zealand is just the emergent highland part of this sunken continent. New Zealand has literally been pushed up within the last 23 million years. So there's a really interesting mystery to be solved here, and that is, could it be that New Zealand was totally submerged just 23 million years ago?
Hamish must come up with irrefutable proof if he wants to convince other scientists that his country was completely submerged before it was thrust up by tectonic forces.
What I'd really like to do is to revisit all the key localities around New Zealand that would enable me to get good sample, the detail I need to help solve this problem.
This hypothesis would have been very difficult to prove even a few years ago, but new dating techniques now allow for the determination of the precise origin of New Zealand's geological matter. It's a challenging task for Hamish. He has to travel the country, from the coast to the top of the mountains. He's on the lookout for rock formations that have recorded his country's underwater past.
What we want to do is have a look at this limestone.
So what you want is right on top, it's not this down here that we're looking at in front of us?
Yeah, if I can just get...
Hamish is on his way to sample the sedimentary rocks of South Island. Formerly undersea, they were squeezed, moved, folded, and eventually elevated to an altitude of 2,000 meters when the Australian and Pacific plates collided.
Okay, here we are.
Hamish hopes that the mountains encircling this plateau have protected the rock strata from erosion. These formations can give him precious evidence to support his theory.
I'm just going round here. I'll just get to the head of this gully. Okay, this is the best place to collect the samples I need. We need samples for microfossil analysis. Okay, this limestone's really very pure. Should do for our purposes. Oh look, got a fossil tooth.
But Hamish is under no illusions. His sampling must be extensive and extremely precise.
You know, that was a fantastic trip. It really was. It was much better than I thought. We've established that there's a really thick sequence there, fantastic story, and I can't wait to get a couple of PhD students there crawling over that. We want to take that sequence to bits, and we're going to throw at it the latest firepower, such as strontium isotopes, and I think we're going to be able to solve this mystery, but it is going to take time.
Hamish must also travel to New Zealand's North Island. Here, the Pacific plate pushes underneath the Australian plate. This tectonic movement is a constant threat to this region.
The significance of this volcanic eruption and the eruption along a considerable length, it's most unusual, but for all that, it relates to, if you like, everyday business associated with the rifting of the crust. If you rip open the Earth's crust, then volcanic material will reach the surface.
On the morning of June 10th, 1886, the biggest eruption in New Zealand's history occurred here on Mount Tarawera. It continued for 4 hours and killed hundreds of people. It left a scar 17 kilometers long. Under the surface of North Island, the volcanic activity never stops. Geysers, hot springs, and boiling mud all show the tectonic instability.
These superheated geothermal waters are coming from really deep down, you know, about 1 or 2 kilometers. And at that level, they're about 300 degrees Celsius. But up here, it's only about 150 degrees Celsius.
It is difficult to believe that life is possible in this hostile terrain. For almost a century, the heat contained in the ground on the North Island has been a valuable natural resource. At this point, 12% of New Zealand's energy comes from the planet's core. The raw energy coming from the Earth's core can be seen clearly in the Ring of Fire. This is where 70% of the volcanic activity on the planet takes place. To the west of Australia lies the Vanuatu archipelago of 80 volcanic islands. Like New Zealand, these islands are located at the meeting point of the Australian and Pacific plates. But what is happening underneath is exceptional. Here, the Australian plate is sinking under the Pacific plate. This phenomenon, unique in the world, is occurring at the astounding rate of 15 centimeters per year. 3 million years ago, this tectonic activity gave birth to new volcanoes like Mount Yasur, which, despite its peaceful air, is one of the world's most active volcanoes. Phillips Mbani was born in Vanuatu. His passion for volcanoes is also his career. Today, he is climbing to the top of Mount Yasur to gauge the gases and the volcanic bombs spewed out of the craters.
That's a fabulous explosion, but it's relatively small. Sometimes the explosions are quite powerful. These volcanic bombs lying around have been spewed out by the volcano. When explosions happen, you mustn't run. You've got to keep your eye on the bomb. You see it coming and try to dodge it. If you run away and a bomb lands close by you, that's even more dangerous. These pieces have obviously come down quite recently, which means we may be in for some more activity. These are small, but you can see big chunks lying around. If the activity continues, we may be in for a barrage of large bombs. It could get dangerous.
For several years now, Phillipson has analyzed the gas plumes coming from the 3 mouths of Mount Yasur. The presence of gases like sulfur dioxide gives him important clues about future eruptions.
What I'm doing is measuring the concentration of gases in the plume. I use a spectrometer that measures light absorption. As sunlight shines through the plume, the various gases in the plume absorb light differently, so I can identify them. I look for sulfur dioxide and other gases. Mount Yasser has three mouths. Mouth A is the one farthest to the left. Mouth B is right in front of us. In fact, mouths A and B are practically within the same semi-crater. Then there's mouth C off to the right, which isn't doing much right now. That could be A. That's B. You can see it spewing all over the place. It's coming right at us.
The speed of the bomb spewed by the volcano can reach 700 kilometers an hour, making close observation extremely risky.
Wow, awesome. Both of them at once. That's amazing. A and B at the same time. Incredible.
By studying Mount Yasser, Philipson-Bani hopes to predict the volcano's future and to understand the ongoing tectonic shifts, the same sort of movements that created the archipelago in the first place. Since the appearance of the first bits of the Earth's crust 4 billion years ago, tectonic forces have never stopped reshaping Oceania. But unlike this wave of rock that will never crash, Australia's future is not written in stone. All over Australia, scientists like Philippe Ray are studying tectonic forces, hoping to discover what lies ahead for the continent.
The Australian continent is unquestionably the most stable continent on Earth at the present time. But in 10 or 20 million years, we can expect a dramatic change in the geology under the perimeter of this plate. On the northern edge of the continent, the process has already begun, with the collision between the Australian plate and the Asian continent. If we were to come back here 10 or 15 million years from now, we'd see a mountain chain, much like the Himalayas, stretching from Bangladesh in the west to southern China in the east.
We now know that Oceania has some of the oldest rocks on Earth. It's where you can see the effects of stromatolites that oxygenized the globe. We also know that it was the cradle of the first complex forms of life, and that later it protected species which were wiped out everywhere else on the planet. As always, the power of tectonics can decide the fate of continents and all those who live on them.